Okay, well, I think we can start. So, as mentioned before, I did some social profiling
Wow.
for the introduction, but it's not so much, just
That's
half a
very
page,
good.
something like that.
Oh, la, la.
Now, it's really a great pleasure for me to introduce Professor Tullio Vardanega to you. He got his PhD in computer science from the Technical University in Delft. And has a long-standing academic career. Currently, he is professor at the Department of Mathematics at the University of Padua, but he also was working, so prior to academic, for the European Space Agency. When I remember correctly, it was 12 years or something like that, or for 12 years, yeah. Right? And he contributed there to the development of real-time and on-board computing systems for space missions. He has a lot of different research interests. He has close to 200 publications, or at least this is the number of publications that's available online.
Oh, indeed.
It's quite a lot, and the foci are software and systems engineering for real-time embedded and dependable systems. And recently, he also engages in innovation in computing education. He was also the president of Ada Europe and contributed to ISO working groups on programming languages and system vulnerabilities. So please join me in welcoming Professor Vardanega.
Okay, thank you very much
for the floor is yours.
Yeah, thank you. And I'm starting the clock so that I don't really overrun. 40 minutes. Clocking down, huh? And when it will ring and say, stop, stop. All right. So I said, thank you for the invitation. This is not a presentation of research results. It might have been, but I chose to take a different angle. That is to say, to use a little bit of the oversight that the lifetime, at my age has, over, how certain elements of what I experience as a teacher, as a professional, crosses education. As in the introduction, after the scavenging, the spying out, Professor Bolin found, my interest, my research in informatics education started more recently than the rest of my career. And I believe that it started as a consequence of wanting at a personal level to understand why informatics should be learned. And I'll tell you a little bit of a story, to sort of a short one, so that you understand why this urge was kind of, growing up in me, and it took years to manifest in terms of research. When I joined the European Space Agency, I was only 4 years into the profession after graduation. Of course, as a graduate in informatics, I thought informatics is the center of the world. Everything revolves around informatics. When I go into European Space Agency, and one of the things that people working there as staff members at the research center, where I went in the Netherlands, is to be a member of space project teams. So there are certain activities out there that have to deliver and deploy systems for space observation, for astronomical observations, for communications or something, and then you find yourself that you are not the center of the world at all. In a typical space project team, which numbers, in terms of controllers, people that are out there to make sure that the science is applied and the engineering are applied correct, not those who do the work, but those who oversee the work, may count 40 people. Of those who have a background in computer science, in informatics, are perhaps 2%. It's embarrassing. The rest is physics, the rest is engineering, the rest is astronomy. Lots of other, So I was there, and I was a minimal part of the thing, I realized that there was so much value in what informatics did to systems. But in fact, in terms of the organization, the social organization, the cultural organization, informatics was a very tiny part. When I went to, after taking the PhD from University of Delft, I said, okay, what do I do in life? And I said, okay, let me try the university part, because education is nice. When I go to university, and in the University of Padua, which is very large, very, very large, is one of those large universities, you don't even find the name informatics. And I came down from the Netherlands to Padua at the end of 2001. And at the time, they were starting to build a bachelor degree in informatics, 2001. And I was told by a colleague, who was the one who sort of said, come join us, that the rector at the time was very much dubious about the opportunity of creating a curriculum in computer science. And he was a philosopher by education. And the story goes like this, they went to him and said, okay, we should be, it's 2001, we should be having curriculum in computer science. That's insane that we don't have it. And he, becomes like the statue of Rodin, the thinking man, thinks. And he says, we are a very old university. We will be nearing soon 800 years of existence. We cannot follow fashion. How can we be sure that this informatics thing will be there for lasting? How frustrating. So that gave me even more of an impulse of saying, okay, how do people understand us? How do people understand informatics? What is the value of that? And then I was brought into lecturing. I like lecturing really because one of my inclinations as a person has been always to try and persuade others, not as a commercial, but intellectually persuading. So that was a nice task I had, but I had no training into education. And because perhaps I'm versed into what the psychologists call metacognition, I was always inclined to try to understand what I understand. If you see what I mean, square of understanding. That brought me into research into education. See, how really can we pass on a message? What is that we want to pass, why it passes, and blah blah blah. And I start seeing things come together. So what's the talk about today? I'm focusing on programming, not because, in fact, if I were to sort of say honest, how much do I believe that programming is important? I will tell you very little, because I believe that it will be less and less needed. However, the understanding of programs, it will not go away. So that is the important part. So not the act of producing code, but the act of thinking code is important. So that is the thread that I'm concentrating on. And trying to sort of seeing two things that are coming together in this talk. And again, they've come together not so much in the talk, but also in my way of thinking. One is being exposed to an understanding of how learning works. So it's not that I studied how learning works, but by working with people that study that thing, I believe I understand some of that. And it is very much important, because if you understand how learning in humans work, then you can find a strategy for teaching. Because if you're trying to teach in a manner that antagonizes the way learning works, I'm sorry, you're wasting time. So that is important. And the other is that I've been for a lifetime, in fact, into software engineering. In addition to, when coming to Padua, created a course and kept it for forever, which is not very sane, in fact, but kept it forever. And then again, I see the obvious links. They're so apparent. And in fact, I believe that statistically, you would find that lots of people who work in, who do research in informatics education have some knowledge into software engineering. So the two things are really sort of in some way nested and paired. And the thread I'm liking to stay on is attributing value to errors. So say errors, don't hide, don't shy away from them, but value errors. Not in the sense that making errors, mistakes is a thing you want to do, but because we all do, the best we can do is learn from them. So drawing value from them. And this sort of learning from errors is so obvious in other disciplines that it should be obvious that it is also applying to informatics education. Now, when I reflect on the teaching that I was given a million years ago when I was young, and the teaching that I often see given, and sometimes I also give, is that we tell students, or they told us students back then, that programs should be right at the first try. And for two reasons, fundamentally. One is that the time to produce a program is too short for a program to form in a manner that is flawless. And number two, because failure is not contemplated in the climate of classes. So when you are implied that when you say, this is my code, it has to be correct. And it is, in reality, it can never be, and it cannot be believed it is correct. So it factors in error, mistakes, And the learning part is this, the value in learning to code is identifying and rectifying errors. This is how you improve yourself. If you don't go through that path, I don't know what you're doing. However, when I'm looking through the teaching I've seen, the teaching I was given, the teaching I have been given, this is almost inexistent. So you see the problem. I'm trying to sort of say, and I believe I say it with a certain degree of insistence because I do believe it, that effort should be paid in that direction. And this is like reversing the logic of most of this teaching. Now, in trying to understand whether informatics is a science, because there are people out there who think informatics is not a science. They are not very, they are the majority. And why do I think that informatics is not a science? Because what they say is the tip of the iceberg. And the tip of the iceberg is absolutely far from science. Although, So there is this person, I think you know him. And Andreas, of course, knows him. But if you don't, look him up. He's a very important figure in the UK. He is the person behind the reform of the education cycle in the UK, giving space to informatics as such, although they call it computing or computer science in the UK. And when he goes around and sort of presses the government bodies, the education bodies, to make room for informatics as a science, he often uses this argument. He says, look, let's consider a hard science. So something that people do not dispute that it is a science, and how it is organized. Well, it is a layer stack, in which, and he shows it not as an iceberg, but like a journey from the air out there and the deep seas. It's a stack that has something visible out there, which are the consequence of science, the things that you can do with science. Call them applications. So these are the products of science that allows, for example, for physics, you build buildings, you fly into space, then you aid medical cure. So this is the top, but in fact this is the top because there is something underneath that sustains it. And in the case of physics, at the bottom, the foundational part, I'm skipping the center, you can read it for yourself, but at the foundation you have the science pillars. And not everyone should be versed in this body, but you will need this knowledge, because without this knowledge, that will not exist. It will exist and it will decay because the developments will surpass it and will be behind. So you need this part. So this is a rather easy argument. So now Peyton Jones is now Sir. So Sir Peyton Jones is rather convincing. Now, does it apply to informatics? Would people understand that this also applies to informatics? So is there this stacking? And we should be persuading people that it is indeed the case, that informatics, which has a very visible top, so pervasive, so invasive, so dominating, but instead of being a pyramid, it's an inverted pyramid. So the visible part is so large. And so, if you like, how would I put it? It appears so easy, in a sense, that you say, this is mechanical, this is electronic. No, there's a nice movie, again, my age, I think this is a movie that was made in the early 90s. So when I bring this example in class with students that were born in 2001, 2002, they look at me like, you're citing a movie from the 90s? This is prehistoric, what is this? We don't know. Anyway, so in this movie there are two persons that by an inexplicable act, they are brought back to 1482. And they are, however, modern people. And they found themselves in a place in which there is no electricity, there is no running water. And they try to tell one, how can we, there's no light switch. Oh, it's easy. We just make, a light switch. Now that's not easy at all. They don't know. There is no running water. Oh, what do we do? So they find themselves that they know that the top, the manifestation of science, but they don't know the science. And they can't fill the gap. So fundamentally, it's like we have so much of the top, and we don't know what it comes from, why it comes from. And of course, we can't imagine what it will lead into, okay? Anyway, so if I were to explain, this is not something that I understood immediately. When I was a student, I had no idea about it. And I say, okay, but I graduated in informatics, and I was not told this in a manner that I could understand. And I was, I think, decent. I was about to say bright. That's too much to presume. I was a surviving student. I was telling over lunch that when I started university, we were about 900. When we finished, we were 7. The year before, we were 12. So by being one of the 7, I thought, gosh, I'm strong, Anyway, this I didn't understand, and it took me years to understand. So I was asking myself, what is at the center of informatics? Now, don't read, and try, each one of us think of the answer. And I believe that the answer is, at the center of informatics, is computability. And again, is this trivial? No, it isn't. In what way this is the center of computer science as a science, and therefore informatics? It is the fact that the products of informatics can be executed. So when people say, oh yes, indeed, so informatics is problem solving, well, not quite. Of course it is, but in a manner that makes it executable. And there are lots of problem solving things that are not executable, that are too abstract. And algorithms have been invented by informatics. No, they have not. They have been there for 1,000 years before, but they were not executable. And does it make a difference? Yes, gigantic, because to make something executable, computable, it has to be precise and ambiguous. You have to sort of predict the effect. There are lots of things that don't require this, in a way, in my relation with mathematicians, now you stop recording because one would say is offensive. Anyway, I'm joking. And don't stop recording, don't worry. There is a joke about mathematicians, especially the pure mathematicians, who say, if reality doesn't match theory, it's the fault of reality. They say it's a joke, but it is, So computability is the reverse of that. In order to be computable, it must be executable by something real. And this something real doesn't understand you. It is not gentle to you. It doesn't make inferences. So that is important. In cognitive psychology, cognitive science, really, there is this understanding that one of the things that we developed as humans in the early age of our existence are called executive functions. That's the term that psychologists use about it. And executive functions are cognitive skills that really make the difference. So that all effort should be made in education to strengthen the formation and the improvement, the augmentation of these cognitive functions. And one of the fantastic things that informatics has that link in so nicely with the development of these executive functions is feedback. Let me go about it in a moment, because this theme will go along. How do we learn? Well, it will come. Fundamentally, we learn by seeing that what we know doesn't match reality. Let me try this again. And I will return to this. Our knowledge increases by encountering reality. And the reality we encounter always when what we expect of it doesn't match what we think we know, because our knowledge is limited. And it only increases when we encounter a reality which is wider and larger and different than our belief. So feedback is the mechanism by which we encounter this stuff. Now, computability is the act of thinking something so that it can be executed. Execution gives you feedback. Does this help? Of course it helps. Of course it helps. It helps in fundamentally lots of these things. So some of the important processes which relate with executive functions are the three that I'm listing there in italics. Working memory is really using our human nature, biological nature, that says that our working memory is limited. So there must be a mechanism to have it be in flow, if you like, with the long-term storage that we have. And there must be some triggers for that. So this working memory needs to be used, needs to be exercised. And it operates on feedback. Second is cognitive flexibility, and it is to be able to know what you don't know. I'm simplifying, but you understand? And not be fixated, I know stuff, and you walk against the wall. And third is inhibition. Inhibition fundamentally, although sounds like a strange word, it is that you don't work by instinct. Because if you're working by instinct, you'll be basing what you think you know, which most of the time is wrong. Therefore, you have to get yourself used to thinking before doing. And the thinking before doing, links very much with computability, because you think before doing. Creating a problem is thinking before doing, is preconceiving an effect and trying to achieve it. So it links in very naturally. Now, back to Peyton-Jones. This perhaps is one way of looking at this, this sort of deep stack of informatics regarding programming and programs. So programming and programs, so programs are the artifact of programming. They have a visible outside, which is when you execute them. We execute lots of programs. You know, I programmed the clock to tell me when I should be stopping. This is a program, and it is very visible. And then programs have a visible inside. That is to say, you look at program code. This is inside. It is not what, you know, it's not the execution. It's what it will at some point execute. It tells you something. But then they have very much more important, deeper down, hidden inside. So before program code, there is something else, something more, something deeper, something more scientific, something more foundational. And it is, as I try to write in this sort of text, it is concepts, things that you can conceptualize. It is methods, ways in which you operate, knowing that you're doing that way, and practices, that is to say, suggestions for what to do, that allow you to develop ideas, concepts, computable concepts, and concatenate them into something which then become, I'm using the term, I don't think I'm inventing it, executable intentions, you know. If I were to rationalize a little bit onto this executable intention, you understand that this links into computability. Having executable intentions, it is very sort of characterizing of informatics. I want to obtain an effect, but it has to be an executable effect. So my conceiving of intentions, intents, goals, has these connotations of being executable. All right, so without you reading so much text, what I'm trying to say is this, and this I very profoundly believe, that in programming, the visible outside is of course very emotionally engaging, but it is so deeply ephemeral, so it's not very important. So it is the effect, but what really retains, what values to your growth, in intellectual growth, is not the visible part, it is the deep element inside, and it is where focus should be placed. So all educational effort into this programming program should be placing at the bottom, focusing at the bottom, using the top, the visible top, to motivate, but not as a goal. The goal is not there. Now, this was shown by a working group in the ETICSA conference. A colleague, an Italian colleague, Violetta, and others were working on this sort of theme. What are programs? Can we establish what they are? They came up with this sort of drawing, which is rather rich and complicated drawing. But it says some of the things that I think relate with our intuition and understanding. Interesting parts without spending so much time on that. A program is there to meet real-world needs. Is this useful? Of course it is, because it speaks of real-world needs. A program that meets these real-world needs is executable. But it is executable at two levels. One is a conceptual level, call it notional, and the other is concrete, by becoming an artifact in one particular programming language. This, I believe, not by mistake, this conceptual model of computation stays at the center, because it is more important than the actual artifact. So, on the one end, a program is important because it meets real-world needs. So you think of a real-world need and you say, how do I make it? How do I make a solution to this need computable? Is this useful? Of course it is. Of course it is. And then, this program becomes useful if it has an algorithm, a computable algorithm. Again, algorithms were not invented by informatics, by computer science. They existed long before informatics make them computable. By what? By agents independent of us, outside of us. So that is brings into the notion of computability. That is, what is really computational? What is computable? Is that everything is computable? No, it isn't. However, lots of things are. And so many things are computable. Let me try this on you, because I'm working on a pet project, which, if I succeed, becomes a piece that goes into a theater, so that there is an actor playing a part and explaining this thing. Computer science, in the foundational moments, the Turing and the von Neumann moments, was concentrating on what is computable, and found that not everything is computable. That was one of the big contributions by Turing, for example. Well, this was the negative result. However, the mathematicians were concentrating on, the hierarchy of infinite numbers. But infinite numbers are so large and so distant, that between here and the infinite, there is so much space that can be filled. So in other words, what I'm saying is, there are things that cannot be computed, but the things that can be computed are so many, because the space from here to what cannot be computed is large, and it is increasing. Yeah? So lots of things can be computed, and because by being computable, it can meet real-world needs. Oh gosh, we should be working on that direction, don't we? All right. When I'm telling students, I don't know whether it happens also in Austria, but in Italy, students in informatics often use English terms without really understanding them, but speaking them without understanding them. So when they say, well, we implement something, and they say we implement in Italian, so you can imagine what the meaning can be, I'm asking them, do you know what implement means? And obviously they don't. And in fact, implement in English has a very sort of interesting and revealing meaning. And it is this, as I report on the slide. So implement, as a noun, not as a verb, is a usable tool, a tool that can be used. So to me, the link is rather obvious. So implementation and implement is a very sort of used, if not abused, term in informatics, because what we do is executable stuff that are tools that can be used. So implement in that sense is an appropriate term. Anyway, so back into the story. If we want to sort of help people learn, we have to understand how learning works. Otherwise, we work against tide and we don't help. So in the process of learning myself into how is our mind working, I cannot intuition is not enough, and intuition, as I said, is mostly erroneous. I've been sort of led into reading books from scientists who understood lots of interesting ways. So this is a masterpiece. If you have not read it, go grab it. It's phenomenal. Have you? Of course you have, but you have? Have you? That's not an exam. You can say no. You're not disqualified. This is a gigantic. It is written splendidly, and it is written not to make you fail to understand. It is written to make you understand and relate what you understand to, oh yes, that's the way I function. The title is evoking the thinking. Fundamentally, this book says the following. we have understood our thinking, not so much learning yet, our thinking process works. And of course, our thinking process relates to biological elements. There is an element which is the brain part, the mechanical part, if you like, how it is organized, and then how that mechanical part is used. So they are called, in this book, for lack of better terms, System 1 and System 2. And then this term stuck also in the literature. System 1 is for survival. Is our biological inheritance. Is there to help humans survive in difficult conditions. So it is for thinking fast. In informatics terms, it's like associative memory, in which you make a query and get an immediate response. However, it is operating on a very small memory, small storage. Because what you need for survival is not very much. And then there is a complement to that, which is called System 2, again in this jargon, which is thinking slow. This is the long-term memory, where you bring in your actual knowledge, and then you use this knowledge to condensate into associative tables, if you like, if you know what I mean. So now, why did I say earlier that we learn by errors? Because, we are born with a System 1, biological inheritance. But this is inadequate to our living, because we live in a reality which is very different from our biological inheritance. Some things are still true. If I get close to fire, I get myself burned. That is still true. If I get close to ice, I get myself frozen. But many other things are not there. So the long-term memory, System 2, is there to consolidate all of the discrepancies that show that our small memory is wrong, elaborate experience, so that they can fill in System 1 with more accurate knowledge, so that we can act fast. So this is fundamentally, well, in a sort of very brief and extremely superficial description. And the mechanism that triggers an update of System 2 and System 1, so the long term on the short term, is feedback. It is the observation that your instinct is wrong. You understand? Otherwise you don't need any maintenance. It's working. So this mechanism, the experience you make of being wrong, triggers a long process which consolidates updates your knowledge, and this then feeds into your System 1. Okay? And it is not me, it's human nature. This is, wow, so very interesting. So very interesting. And it's biological, you see what I mean? So feedback gets a very important role in here. In triggering this. By the way, other books of science tell us that the moment in which our differential experience, when we sort of put this feedback into, we elaborate on that, is when we sleep. That's another book, I'm not mentioning it. This is a phenomenal book, another one. The title of that book is Why We Sleep. And the fundamental story of that book is, if you think how much humans spend in their lifetime sleeping, you would be amazed. Sleeping very little, In fact, on average, we sleep 1/3 of our lifetime. And then this sort of researcher says, what's the point of sleeping? It would be wasting time. So there must be some good reason why biological evolution keeps sleeping as a must to such a large extent of our living life. And then he says, what happens when we sleep? Most of the time, it is System 2 working. You understand what I'm saying? So the thinking slow cannot happen when we are active. It happens when we are inactive, because it is a long energy-consuming process. So that is this important element with LEAP, system 2 systematizes the new knowledge, creates associative tables that can be placed back into the short-term memory to guide us into instinctual level of reasoning. Wow, this makes a lot of sense. And what is the triggering moment? Feedback. And feedback is caused by what? Mistakes. Situations in which what we do doesn't match what we expect in the outcome, in reality. Hola, what am I doing? So very nice, so very nice. So this is, now let me, if I'm reading this, don't read the text, only concentrate on the boldface. Execution, feedback, retrospective, improvement. So these four terms, and you say, okay, where do I must have seen somewhere else. Where have I seen them? Execution, feedback, retrospective, improvement. Well, I've seen them in at least two places. One is extreme programming as a practice. Now, extreme programming, what is it doing? You know, one of the practices, which is sort of finding some sort of consensus that it may work in software engineering. It is building on feedback via the very important moment, in fact, they call it ceremony of retrospective. So this is, they are not inventing anything. They are kind of realizing how our biological mind works and leveraging that mechanism. So execution and feedback, they have to be linked. If you have an execution and no feedback, that's not very useful, because it only uses system one without improving anything. Feedback moves the cycle. However, this moving the cycle, this tells me, oh, you man, you know, okay. Let me come to silence this, and then I'm drawing to a close rapidly. Don't you worry. So this is.
I think you can have 5 minutes more.
I may need 5, but no more. So this you need very often, and in fact, if you, how often in extreme programming, in agile processes, do they have this cycle? We say every sprint. Every sprint. And are sprint long? No, they are not. They are short enough. Why? Because we need feedback. We need a lot of that. So education into anything would have to give feedback. But of course, there is a problem. Feedback is individual. If we make feedback synchronous, when I tell you, that is not working very much. So an education system that builds on this should be favoring feedback on a personalized manner. Right? And what should be regulated is not so much the feedback, but it is the retrospective, which in fact is called a ceremony. It's a liturgy. A retrospective is a collective moment, whereas feedback is personal. Retrospective is a collective moment. It is a guided moment in which you are helped understand what you learned. And in fact, learning what you learned is called metacognition. You understood what you understood and why you understood it, which makes it retain. Wow, so that makes it an interesting link to draw it to a close. You know, I don't know whether you read this book. Have you? So this book is a classic, and it's very ferocious. You know, this book is very ferocious on how stupid we humans are. And this passage, I find it fascinating. I always show it in class because students misunderstand completely the point, exactly like this quote says. You know, they want to build something because the emotional satisfaction they get in having it, you know, it compiled, fantastic, you know, and it is completely useless, completely useless. Anyway. So that is the story. The story is the other moment in which this sort of execution, feedback, retrospective, improvement is used is in the self-improvement cycle, in the continuous learning process. You know, that is why, because it is exactly the same thing. So let me go back into this and then I'm closing. I'm not a tennis player. In fact, I dislike tennis. But I'm amazed at some of these super champions. So last, when was it? 10 days ago, this Yannick Sinner, Italian, northern Italian, won at Wimbledon. And I'm looking at this man who's a robot. And he was sort of saying, I lost this final in France, Roland Garros, and it was a disaster. Well, what did he do? Feedback, retrospective. He concentrated on why he lost. He understood together with his coaches and why we lost, and next time he wins. This is not superstar. This is not super. This is what we should be doing, understanding why that was wrong. Being helped to understand why that was wrong, and next time we make it right. So what I'm saying, and with this really I'm closing. Feedback should be personal and immediate, which means it has to be from small assignments, and it has to be asynchronous. I cannot tell you when you have feedback. Retrospective is the central moment. You have to be guided and aided into understanding, and this can trigger this phenomenal self-improvement moment. This is, Anyway, so that is my recommendation. Hopefully one can build a system of learning which works in that manner. Okay, and this closes the talk.
Okay, then thanks a lot for your presentation, and also thank you to the Förderverein Technische Fakultät who made the presentation possible. So
Indeed, yeah.
thanks a lot, and let's give you applause.